There was a time, and it wasn't that long ago, when people would be digging in the hills, maybe putting in a house or a garden, or just playing, moving rocks and dirt, and they would come across something different, something that wasn't rocks or dirt. It was often stuck in the rock and sometimes just laying there by itself. It was hard, usually shiny, and you could work on it without it fragmenting and falling apart like rocks did. Plus, it could be melted and shaped, and there were several different kinds of this stuff. It was metal, usually gold or silver or copper, just lying around or embedded inside of the rocks. This was great stuff and valuable because with it you could make things like tools and knives. Was there more of it? And why was it so different than everything else? These kind of questions and these discoveries were the beginnings of what we call chemistry. Chemistry is often called the central science because it connects all the other natural sciences like astronomy and geology, biology, and physics. So, just what is chemistry? When we think of chemistry, we often picture someone doing this. And in reality, I suspect you will seldom catch a chemist staring into a beaker of colored liquid, except when posing for photographers. And apparently, lots of photographers believe that this is what chemists do because you see lots of these kind of pictures. Technically, chemistry is, quote, the study of matter and energy and the interactions between them. That oddly enough happens to be the same definition for physics, the study of matter and energy and the interactions between them. So, what's the difference between chemistry and physics?
Well, imagine if the universe was this pocket watch. Physics examines the movement of the hands and the springs, the forces that cause it to wind and unwind, the sound of the ticking, the light passing through the face. And what is sound and time and light anyway? Physics is the physical mechanism, the universe, and how it works. Chemistry, on the other hand, disassembles the watch, disassembles the universe into individual components, the minute, the hour, and the second hand, the pieces and the parts. Then the chemist tries to reassemble the pieces to make something new and different. Can we reassemble the pieces to make different watches? Or maybe even something that's not a watch at all, like cufflinks or jewelry or earrings. Or let's take another example, this toy truck. It isn't a single piece of plastic, is it? No, it's made up of several components that were put together to assemble the truck, and it can be disassembled again. For example, here is the bed of the truck, and the cab of the truck, and the frame. And the cab itself can be broken down into smaller components, like here's the light and a little yellow piece, parts that were found in the original toy box. When you finally come to a component that can't be broken down any further, you know you've arrived at a basic toy part, a basic toy element that can't be broken down anymore, unless of course you hit it with a hammer, in which case it ceases to become that toy part. Like here's a wheel piece, a light, a red brick, and so on. Now that we've got these basic toy elements, we can build completely new things that we couldn't when it was still formed into a truck. For example, we could make a spaceship or a building or a completely different truck. Once you disassemble it, you can make completely new and useful toys. But you have to disassemble it first. The world of chemistry is similar to these toys. We come to things in our world, grass, water, the air, the couch, and we break them down, just like the watch and the truck, separating them into smaller and smaller components until we arrive at the basic parts that built it in the first place. In fact, the motto of early chemists was, in Latin, solve et coagula, separate and join together. Solve et coagula. And that is what chemistry is, the art of separating everything into its individual pieces or elements, then recombining them to form new substances. Now, it is true that much of chemistry can be very complex, requiring a great deal of hard work, years of study, a lot of complicated math, and yes, probably some staring into beakers of colored liquid. But it is also true that a great deal of chemistry can be fun to study and understandable by just about everybody, even if you don't know the complicated math. And that is the area of chemistry that we want to explore. In the first part of Chemistry 101, we will look at the amazing stories of how we started breaking the components down until our journey ultimately arrived at this, the periodic table of the elements. Hopefully you didn't give in to despair when you saw this, because that is a common first reaction. And there's absolutely nothing about the periodic table that says user-friendly on it. In fact, the only thing that most people understand when they first see this table is the word table. But I am certain that by the end of Chemistry 101, you and the periodic table will actually become good friends, that you will understand what it means, how to read it, and even how to explain it to somebody else. Then in the next sections, we'll go a little deeper into the chemical world, even to introduce you into how to balance chemical equations, which look something like, brace yourself, this. 2Mg plus O2 equals 2MgO. Huh? And what in the world do those ball and stick things mean? Well, we'll find out. Then we will take a fascinating tour of every single element on the periodic table. And finally, we will end with the future of chemistry. Our first segment on the road to the periodic table is called The Last Alchemist and spans nearly 5,000 years of history, from ancient times all the way to the 1700s. Nobody really knows what processes were used by the ancient chemists, or what the order of discovery was, or who they even were. But it is interesting, in the book of Genesis, chapter 4, we find this historical statement. As for Lamech's wife Zillah, she bore Tubal-Cain, an instructor of every craftsman in bronze and iron. Nearly at the beginning of recorded history, this man, Tubal-Cain, is specifically identified as a worker in iron and brass, or bronze. In other words, he had some kind of understanding of chemical metallurgy, because while you can get iron straight out of the earth, bronze and brass are alloys and require some pretty sophisticated understanding and skill in order to actually produce them. We are even told his mother's name, Zillah. He was the son of Zillah, or in Hebrew, Barzillah. And not too surprisingly, the Hebrew word for iron is Barzil, the son of Zillah, Tubal-Cain, one of the first workers of iron and other metal alloys. By the way, in Roman mythology, the name of the god of metalworking is Vulcan, which is thought by many to derive from this man's ancient name, Tubal-Cain. Tuval-Cain, Vulcane, Vulcan, the Roman god of metalworking. At least 7 metals have been known since the beginning of recorded history: gold, silver, copper, lead, tin, iron, and mercury. All but mercury are mentioned in the Bible. But what were these metals? And were there more? And how could you find out if there were other metals? And what could you do with them if you got them? What happens if you disassemble the watch? What is everything ultimately made of? These were the questions that men had been asking for centuries. What ultimately makes this leaf up? How is it assembled? What is it made of? If I had a pair of atomic scissors and could continue to cut this leaf in half over and over and over again, what would I eventually find? Many cultures considered this question and developed a set of elements from which everything was made. It was essentially their early version of the periodic table. The Chinese considered this and determined that everything was eventually made of just 5 elements: earth, water, metal, wood, and fire. The Japanese considered this and thought that the basic elements that made up the universe were earth, water, wind, fire, and the void. The Hindus and the Buddhists were a little more on the physics side of things, and they said the basic elements were earth, water, wind, fire, sound, light, dark, and space. And the Greeks, where we get much of our Western civilization, also developed their early periodic table and thought that all matter was made from 4 basic elements called earth, water, air, and fire. They called them the 4 essences. They also thought there was a 5th element or essence that sort of bound them all together. They called it the ether and said it was the quint or 5th. Quint is Greek for 5th. It was the quintessence, which is where we get the word quintessential, meaning it was the essence that bound the other 4 together. Today, quintessential means the most typical or the most perfect example of something. Like, the rose is the quintessential symbol of beauty. Or, the quintessential symbol of freedom is the Statue of Liberty. The quintessence, the 5th essence. This idea that everything in the universe is made of 5 or 6 elements pretty much dominated all inquiry into this field for the next 2 millennia. It's pretty easy from our 21st century vantage point to look back at some of these early thinkers and think of them as pretty unsophisticated. But in reality, many of them were geniuses. And if they were alive today, they'd be internet billionaires, world leaders, or Nobel Prize winners. We see further today simply because we are standing on their shoulders. Before we move on, there is one more Greek who we should probably mention, named Democritus. Democritus thought that perhaps even the basic essences, earth, air, water, and fire, were themselves made out of even smaller, uncuttable, indestructible mini-particles. Now, the Greek word for cut is tomos, to cut, and the Greek prefix for no or not is the letter A. So when Democritus said that these particles were uncuttable, he said they were atomos, atoms, the uncuttable elements. But theorizing an idea like this is one thing. Actually proving that it is, well, that would be another 2,000 years before that would happen. Nearly every ancient culture combined early ideas of chemistry and physics with spirituality and astrology. They were trying to find the unifying idea that would give them new potions and substances, a fountain of youth for the elixir of life to achieve immortality, or maybe even the universal solvent that could dissolve anything. The early history of alchemy is hazy, but the Arabs learned it when they invaded the Greek-dominated country of Egypt around 650 AD. As a result, for the next 1,000 years, alchemy thrived mostly in the Arab world. In fact, the Arabs called this skill the art of Egypt, or the alchemy. Alchemy, the art of Egypt.
And this Arabic word, alchemy, has come all the way down into our sophisticated 21st century laboratories. Alchemy, chemistry. Alchemist, chemist. Alchemy, the art of Egypt.
Much of the alchemist's work was shrouded in secrecy and the occult and astrology. It was considered an essential part to try to understand how creation had been put together. In fact, up into the 1500s, alchemy, to one extent or another, was practiced by nearly every serious scientist and school in the world. Even such luminaries as Isaac Newton, Thomas Aquinas, and Roger Bacon worked with alchemy to one degree or another. It was the science of the day. Probably the major quest for most alchemists in the world was the search for the philosopher's stone, a legendary substance that could turn ordinary metals into valuable silver or gold. The alchemists had other ideas as well. In addition to the four essences plus the quintessence, many alchemists proposed a fire-like substance called phlogiston. Phlogiston was responsible for the ability of things to burn. The word phlogiston even means burning up. Metal, paper, and wood were rich in phlogiston. Dirt had very little. When things burned, they give up their phlogiston and generally weigh less than before. For example, when you burn a candle sealed under glass, like this water seals the glass here, the flame eventually goes out. Why? Well, according to the alchemists, as the candle burns, it gives off phlogiston, and the air can only absorb so much phlogiston. When the air gets saturated with phlogiston, the candle naturally goes out. Makes sense to me, and it made sense to a lot of alchemists too. What was really happening was yet to be discovered. The alchemists were constantly making clever glass containers to heat and distill and separate substances, and then to collect the distilled liquids and solids. The very first substance to be chemically discovered was phosphorus. It was first isolated in 1669, over 300 years ago, by Hennig Brand, a German physician and alchemist, by exhaustively boiling, filtering, and otherwise processing over 60 buckets of urine. Yeah, it's gross, but it was the first chemically isolated substance. Thankfully, phosphorus is now primarily extracted from phosphate rock. Even today, chemists are constantly heating things up in order to separate chemicals one from another. Take simple salt water, for example. They wanted the salt, and they knew it was in there because they could taste it. But how are they going to separate it out? Distillation is probably the simplest and one of the oldest procedures to separate minerals out of liquids. In fact, distillation probably accounts for over 90% of all the separation processes done in the chemical industry today. Here is a simple distillation procedure. Mix up some salt and water. Then heat it up using your advanced alchemist heat source and bring the water to a boil. Boiling produces steam, an action which naturally separates or distills the pure water and leaves the heavier salts behind. A larger lid will catch even more water as it evaporates. The pure water or other substances can then be captured and concentrated even further. They made essential oils by distilling flowers and plants to get the concentrated extract, like rose oil to use for medicine. They advanced the knowledge of ore refinement and made paints and dyes and cosmetics and ceramics. And they made stronger acids, stronger than they could normally get out of simple fruit juices like lemons or oranges.
For example, gold is a very stable metal and resists even the strongest acids. But the alchemists invented something they called royal water, or aqua regia, a nasty combination of nitric and hydrochloric acid, enabling them to dissolve even gold from the surrounding materials. Then later, they could recover the gold from the aqua regia. In fact, prior to 1980, all Nobel Prize medallions were made of solid 23-karat gold weighing just over 6 ounces, worth several $1,000s in today's gold prices. The Hungarian chemist George de Hevesy was working with 2 other chemists who had won these gold Nobel Prize medallions, Max von Lohe and James Franck. When Germany invaded Denmark in World War II, the scientists had to quickly leave, and de Hevesy wanted to hide the medallions, but couldn't come up with a safe place in time. So, he grabbed a bottle of aqua regia and completely dissolved the gold medallions in the acid to prevent the soldiers from stealing them. De Hevesy placed the solution on a shelf in his laboratory at the Niels Bohr Institute and left. After the war, de Hevesy returned to his laboratory to find the solution undisturbed, and he proceeded to chemically separate the gold back out of the acid, which was still there in microscopic form. The gold was returned to the Royal Swedish Academy of Sciences, and the Nobel Foundation recoined the metal into new medallions and presented them back to von Lohe and Franck. The alchemists never did find the elixir of life, or the universal solvent, nor were they able to transmute lead into gold or anything else. Alchemy had pretty much been stuck in first gear for a long, long time. But their observations and experiments made alchemy the unquestioned forerunner of modern chemistry. Then, in the 15 or 1600s, there was a movement that transitioned Europe from the Middle Ages and affected nearly every area of literature, philosophy, art, politics, religion, and science. It was a movement called the Renaissance. It had been nearly 5,000 years since the forges of Tubal-Cain had first produced metal alloys, and in all that time, alchemists had produced only moderate success in advancing their science. And it was about the time of the Renaissance that some were becoming skeptical of alchemy's future. In fact, in 1661, the alchemist Robert Boyle published a book and actually titled it The Skeptical Chemist. This book became the springboard for modern chemistry. And before we go any further, I know the question you are all asking right now: what's with the hair? Why do we see so many portraits in this era of guys with huge hair? I know this is a little off topic, but people keep asking, so we might as well address it. Well, who drives the fashions of the day? Usually it is the rich people, the powerful people, and the popular people. And in the 1600s, those people were the kings and queens of Europe and England. And in the 1600s, the kings of Europe were particularly fond of wearing wigs. Big wigs, which, of course, is how that phrase came to refer to people who are rich and powerful. The big wigs, because they actually wore big wigs. Thus, it was nearly a cultural and social obligation to wear the best wig you could possibly afford when you were going to court or going to have your portrait painted. But by the 1800s, wigs fell out of fashion in the United States and France. That's why you often see early portraits of United States colonialists with wigs, and later portraits with no wigs. Here is a sculpture done of Robert Boyle without the wig. Okay, now back to the skeptical chemist. Robert Boyle, the skeptical chemist, was an amazing figure in science. He is usually regarded as the last alchemist and the first truly modern chemist, the father of modern chemistry. In his book, Boyle presented his idea, based on experiments, that matter indeed consisted of Democritus's undividable atoms, and that every phenomena was the result of collisions of these particles. All his work was groundbreaking. He worked with the brilliant physicist Robert Hooke. And together they invented the modern air pump, which he used to prove a relationship between pressure and volume. Which means what? It's like this. If you take this balloon deep underwater, it will begin to compress and take up less volume because the pressure underneath the water is so much greater, right? Likewise, if I take this balloon several miles up into the air, it will begin to expand and get bigger. Same amount of air, but it'll take up more volume because there's less pressure up there, right? Same amount of air in the balloon, but the volume increases or decreases depending on the pressure on the balloon. This, not surprisingly, is called Boyle's law. So what does this have to do with atoms? Well, this information helped Boyle prove that matter really is made of tiny particles called atoms. Boyle demonstrated that because you can compress the air, there must be space in the air, space in between the atoms. And because liquids and solids don't compress as easily, there must be less space between their atoms. Boyle also knew that gases expand when heated and contract when cold, a fact that you can easily demonstrate with an empty bottle and a quarter. Keep the bottle in a cool place like outside overnight or a refrigerator. The air inside will get cold and contract, and so more air will fit inside. Now, you'll notice on the periodic table there is no element named air, because air isn't an element. The air we breathe is actually a mixture of element gases, about 78% nitrogen, 21% oxygen, and the other 1% is mostly made up of the noble gases, especially argon. So, everybody is mostly breathing nitrogen, which helps dilute the 21% oxygen that we need to live. Then, take the bottle and moisten the rim with water and put the coin on top. As you wrap your hands around the bottle or place it in a small amount of warm water, the air inside will begin to warm and expand. As the pressure slowly builds, the coin will click up and down as the heated and expanding air escapes, thus demonstrating that gases contract when cold and expand when warm. Boyle's careful experimentation seriously challenged the classic notion of the four elements and of the phlogiston theory. Boyle said that science should be separated from the mysticism of alchemy, and he advocated rigorous experimentation and record-keeping. He believed that all scientific theories must be proved by experimentation and must be repeatable before being accepted as scientifically true. In fact, Boyle even invented the term chemical analysis. It was this clear break from the occult of alchemy and becoming thoroughly scientific in his experiments that was probably Robert Boyle's greatest contribution to chemistry. Interestingly, what drove Boyle to be rigorously analytical in his science was his belief in, of all things, God. Historically, this is the case. And why is this? Because Boyle believed that God had created a universe that was logical and that made sense. It wasn't random, it was designed, and it was designed to be understood. To quote Boyle, God would not have made the universe as it is unless He intended us to understand it. This combination of being a committed scientist and a firm believer in the reliability of the Bible really made Boyle quite an interesting person, someone who early on bridged the gap between both sides of the debate. Throughout his life, he spent large sums of his personal finances supporting Christian missionary work and translations of the Bible. And throughout his scientific life, he spent the mornings reading the Bible. And during his own lifetime, Boyle was a famous man, and the King of England repeatedly offered him high government positions and titles, like Duke and Baron. Boyle humbly refused all titles and turned away from public office and fame. It was his preference to be known simply as Mr. Robert Boyle, a Christian gentleman. Boyle wrote, "The vastness, beauty, orderliness of heavenly bodies, the excellent structure of animals and plants, and other phenomena of nature justly induce an intelligent, unprejudiced observer to conclude a supreme, powerful, just, and good author." When he died in 1691, his will provided for a series of annual lectures to be given. Lectures, incredibly, not on science, though that was his passion, but on something that he thought to be infinitely more valuable. The money was given for a series of lectures to be given on the defense of the Christian faith, providing rational and historic answers which demonstrated the truthfulness of the Christian religion. The Boyle Lectures are still held every year in London, England, and today chemists worldwide honor Robert Boyle as the co-founder of modern chemistry. Many consider him one of the 10 greatest scientists of all time. He died at the age of 64 and is buried in the churchyard of St. Martin's in the Field in London, England.